Now that we know a little bit more about derivatives, we're going to start talking about a function and the graph of the function along with its derivative. So this graph that we see right here is the graph of y equal f of x. So it's our original function. Now what we want to do is we want to come up with the graph of the derivative. So this is our original. Now what we can do is we can kind of analyze what we see here in the original graph in order to try and figure out something about our derivative graph. Couple of things to remember: derivative is the slope of the tangent line at any point along the curve. Well, these are straight lines, and so if I have a straight line, I know that the slope of this straight line is actually going to be the value of the derivative. So they're their own tangent lines. So the tangent line to this graph is the graph itself here, here, and on the green line as well. So let's go ahead and start looking at each of these pieces individually. When I look at this red segment, excuse me, I'm not sure what was downloading there. When I look at this red segment, let's go ahead and have a look at that slope. We can see that it drops 1, runs 1. So I know that the slope of this line is negative. So the slope here is equal to a -1. That tells me then that the derivative is equal to a -1. So if I want to graph the derivative function, what's happening here is the derivative is equal to a -1 along all of these points. So here's my -1, and so up to this point I know that my graph is equal to a -1 for f prime of x. So my f prime of x starts here. So this is the graph of f prime of x. Now why is this a hollow point? We'll talk about that in a minute. For this next segment, my slope is rise 1, run 1, so slope is equal to a +1 here. So that would mean the first derivative equals a +1. So at this point, from here to here, this is going to go to a +1. Now we'll talk about the endpoints here when we get done with everything. Over here I can look at the slope and I can say, okay, I drop 1, run 2, so my slope is a -1/2. That tells me that the derivative on this interval is equal to a -1/2 as well. Well, -1/2 is down here in the y region, and have a hollow point here right to this point, and then that graph continues on, we'll assume. So now why do I have these hollow points? Well, if I start thinking about the tangent line at this point, it looks like this could be a tangent, looks like this could be as well. So there's an infinite number of tangent lines at a sharp point. Now this also happens at a cusp in a graph. This is not a smooth curve, and we'll talk about graphs with a smooth curve here in just a little bit, but there's an infinite number of tangent lines at a sharp point. And since I have this infinite number of tangent lines, that tells me that at this point I can't say what the slope is. Is it 1? Is it -1? Is it something in between? So that's why I have these hollow points. Now, it also means that the function is not differentiable at -2. So let's have a look at what's going on with -2. If we look at the limit as, let's say, x approaches -2, and let's approach -2 from the left and then the right. So the limit as f approaches -2 from the left, we can see that this is approaching, oh, I'm sorry, I have the wrong graph here, f prime of x. So the limit as x approaches -2 from the left, we can see is equal to a -1. The limit as x approaches -2 from the right of the derivative, we can see is equal to a +1. And these are not equal, so therefore the limit as x approaches -2 of my derivative does not exist, because the limit from the right and the limit from the left are not equal. Because the one-sided limits are not equal and the limit doesn't exist overall, this implies something very important. This implies that f prime of -2, the derivative at -2, does not exist either. So in order for the derivative to exist, I have to make sure it's differentiable at that point. This one isn't because I have that sharp point. Same thing's going to happen here because I have an infinite number of tangent lines, so that's why I have hollow points here as well. So this function is not differentiable at -2 and 0 because of those sharp points. So this is an example of using straight lines and trying to relate the graph of the original function to the graph of the derivative. Let's go ahead and look at another graph. This one's going to be a parabola. Actually, let's do one a little bit more complicated than just a parabola. Let's look at a graph where we have some curves. So for this example, we're not using sharp points that we have to be concerned about. This is a nice smooth curve. So here we have the graph of a function. So what we want to do is sketch the graph of the derivative. Well, we can do this if we kind of can analyze some very important features of this graph. Now this is a sketch of the derivative. This is not an exact replica of the derivative. So let's go ahead and look at a quick animation that shows us what's going on with the tangent lines in this case. So this is the same graph. What I want to do is I want to look at the tangent line. So if you notice on the left hand side of this graph that tangent line is moving, I can see that I have positive sloping tangent lines. Now as I'm moving this up, I can see that it continues to be positive. It gets a little more shallow, and then right here at this very top point something very important happens. The slope of that tangent line is going to be flat, which means the slope of the tangent line is 0. And it looks like to me it happens right here at -3. So -3 is an important point that we can look at for this graph. Now my tangent lines switch to negative slope, and then here they bottom out again, and here I have a slope of a tangent line that's equal to 0 again. My tangent lines switch to positives again, they hit 0, and then they go negative. So those are some important features of the graph. Let's use those characteristics to look at the same graph and note some of these ideas. So here, whoops, I better make that a little bit higher. The slope of the tangent line, f prime of x, equals 0. And that's occurring right here at -3, so that tells us that -3 equals 0 because the derivative is equal to 0 at -3. Now this is the graph of my derivative that I have sketching over here. Now the same thing happens over here. F prime of x equals 0 here at -1, so I know that my tangent line or my derivative graph is going to cross here as well, and the same thing happens here. So this is where my derivative equals 0. So when you're looking at graphs, that's probably one of the easiest things to start with, is to figure out where your graph crosses the axis. Now remember, over here my slopes were positive, so that means f prime of x is greater than 0, or it's positive. On this interval between -3 and -1, I have negative sloping tangent lines, so my slope is negative. F prime of x is less than 0. Here I have positive, slope is positive, f prime of x is greater than 0, and then my slope to the right of 1 is negative, so f prime of x is less than 0. So now that I have this type of information, I should be able to start sketching in a general graph of that derivative. Now there's some other characteristics of graphs that we'll learn in a little bit in another section, but for now we're just doing a general sketch. So as we look at this, I can see that I need to have my graph, my derivative graph, above the x-axis, above 0. So I can see that I'm probably coming in from this direction with that positive sloping tangent line to this point. So what we have here then, so again I'm above the x-axis here. Now between -3 and 1, my slope of my tangent lines are negative, so that means I need to be below the axis here. Now it could be going like this, but I know at -1 that I have to switch back to above the x-axis. So I know it can't be continuing to go in the negative direction. I know it's going to have to make this bit of a loop, because at this point then I have to be above the x-axis. Now I don't know how low I go. I could go way low down here, I'm not sure, because again this is just a general sketch. Now from -1 to 1, my derivatives are positive, so this graph comes in something like this, And again, it could go really high, it could be low. And I know it just doesn't go on positive forever because it has to switch to negative, and it will switch to below the x-axis. My slope will be negative from 1 to infinity. So it matches up here pretty specifically. So where did this come from again? The derivative is greater than 0. The graph of my derivative has to be above the x-axis. It has to be greater than 0 as well. From negative 3 to negative 1, my derivative is negative, so I know I have to be below, and I know it has to loop back up because it has to switch to positive on this interval and over here as well. So that's the general shape. And now it could go higher, it could go lower. I'm not exactly sure, but again, this is the general sketch of the derivative. The original function was the black graph. The derivative is the red graph. So let's go ahead and look at an animation that shows us kind of some of these same ideas. So as we look at this particular graph, we can see the slopes of the tangent lines are being drawn. And as we look at the slopes of the tangent lines, we can see the transitions for that 0 slope, that horizontal slope. And we can see that those points are occurring at negative 3, negative 1, and 1. Now what we can do is we can try and sketch that in based on the same information. Let's see if we can get that to draw from the original. So let's draw our graph of our derivative. So our graph of our derivative is this red line, and it's relating those transition points and our slopes. So our slopes switch positive and I'm above the x-axis. Our slopes switch to negative and I'm below the x-axis now. So that gives us a good idea of what's going on here. Now you can also see these important points. Where is the derivative equal to 0? Where the slopes of the tangent lines equal 0 are at these 3 points, and these are 3 important transition points or solutions to my derivative graph. This is an example of some of the things that you can find in your e-text. If you want to look in your e-text, it's under chapter contents in my math lab if you haven't checked it out yet. I think it's a pretty good resource to use. Let's go ahead and look at one more graph. Okay, so remember, for these problems we're just doing a general sketch. We're not going to come up with the exact graph yet. That's going to take a little bit more time for us to develop some more ideas. So let's go ahead and look at these slopes of our tangent lines. You can see we have this red line right here that is our slope of our tangent line. And to the left of this vertical asymptote, and the vertical asymptote will stay for both the original graph and for my derivative graph. So for my derivative graph, and I should write down what my directions are here, sketch the graph of the derivative. So for my derivative graph, and I'm going to write that in red, these vertical asymptotes will stay, because my original graph is undefined at these points. The derivative cannot pass through these points either. So here I can see that to the left of this this vertical asymptote, I can see that I have a slope of my tangent lines are negative. So my slopes are negative over here, so that means my derivative is also negative. So that's some good information. Now over here, my slopes of my tangent lines continue to be negative, so my derivative is also negative. On this side, however, my slopes are positive, so my derivatives are going to be greater than 0. Then over here you can see that my slopes are negative again, so my derivative has to be negative, has to be less than 0. So that's some interesting things going on. Now here I also have my derivative is equal to 0. So that means if my derivative is equal to 0 at this point where this occurs, I'm going to cross through the x-axis. So this directly relates to this value of x. Now I'm not exactly sure what that value of x is. It looks like it's somewhere between 0 and negative 1. But this is kind of a close enough idea. Again, it's just a curve sketch. So let's go ahead and try and fill in the blanks here. To the left of this vertical asymptote, my graph has to have negative slope. Well, I think the only really way that we can look at this and have that occur is if I almost have not an exact replica, but a pretty close replica to this shape. Now one thing that we're not seeing here is we do have a horizontal asymptote occurring in here somewhere. We can't come up with that value on our own because we don't know what this function is. We're just given a sketch, but we could estimate it if we wanted to. we could estimate that slope to be, let's say, at or horizontal asymptote to be somewhere at maybe -1/3, but we don't want that to end up coming into play as a huge part here, because that's just a guess. So as we sketch this graph, we have to always be below the x-axis, and I have to approach this vertical asymptote. So it's going to be something like this. Now over here I need a negative part to my derivative, so I have to be below the x-axis, and then at this part I have to switch to being positive from here, so I'm above the x-axis, and it's going to approach these vertical asymptotes from either side. Now over here my derivative is less than zero, so that means my graph has to be below the x-axis, and that vertical asymptote in here kind of gives me some direction as to where that would have to be. So you just piece these together based on the important pieces of information like asymptotes, slopes of the original graph of the tangent lines, and also where derivatives are equal to 0, where I would have that slope equal to 0. So again, these are sketches for now. These are just quick sketches of what the derivatives look like. Now one of the main reasons that we start talking about the graph and the derivative of the graph, and of course I should write here that f prime of x is in red, just so we remember which is which, is we like to be able to talk about differentiability. And we can see that this graph is not differentiable at x equal -1 or x equal +1. And then we kind of wonder if it's differentiable out in these areas as well, and it is as it approaches these values. But the vertical asymptotes are definitely a problem. So let's go ahead and talk about the connection between continuity and differentiability, because it is important. And what we want to come away with here are a couple things. If f is differentiable, if my function f is differentiable, then what that happens in is that point A that I'm looking at on the particular graph, then the graph of the original f is also continuous at A. And that's kind of what we showed up here, is if I have continuity at a point, and we know the definition of point continuity, I also have differentiability at that point. So it's important that we be able to look at that and talk about whether a graph is continuous and differentiable. Let's go ahead and look at a quick graph again. I like looking at these visuals instead of just the good old definitions. Of course, this is our y-axis, our x-axis. We could look at something, let's say like this, and like this. And this is my point. Let me scoot that over just a little bit. And this is the point A that I'm interested in looking at. And if you can see, my graph is discontinuous at x equal a, and this is because the limit as x approaches a of my function does not exist. Now the reason it doesn't exist is because the limit from the right and the limit from the left are different. So if you had to explain this on a handwritten homework or a test, you'd want to be very thorough with that. Go ahead and say, yeah, the limit doesn't exist because I checked the limit from the left and the limit from the right and they don't agree. So since f is not continuous, since my function is not continuous at a, it's discontinuous at a, then what that means, this implies f is not differentiable at a. Okay, so because I have a discontinuity, I don't have a continuous graph at a, that means I'm not be able to differentiate at a either. This is going to be an important idea. Now another thing that we could say here, just to kind of make this a little bit more clear, is we could say not continuous implies not differentiable. So that's basically what this theorem is saying. But we have to be really careful about something here. A lot of times, because we say, okay, Not differentiable, not continuous. We'd want to say, okay, if it's continuous, it's differentiable, but that's not true. If we look at the graph of y equal the absolute value of x, it's continuous, and let's go ahead and put this is our value of a. It's continuous at a, but not differentiable at a, because of that sharp point. So basically what I have here is an infinite number of tangent lines at a. And because I have an infinite number of tangent lines at a, how can I find the slope of the one tangent line? So that's kind of our issue here. We can't say, okay, if it's continuous, it's differentiable. That's not a true statement. So again, we have all these different tangent lines at this point because it comes to that sharp point instead of being able to come up with that horizontal tangent line as the only tangent line. So caution, be really careful. Do not say continuity implies differentiability, because that's not what we're saying. So continuity does not equal differentiability. So this is only not continuous, not differentiable. I can't switch it to the other way. Now if you want to think about these, there's actually kind of a logical thought process here. You can talk about a contrapositive of a statement, but you have to be really careful about how we talk about the opposite. So again, be very careful. This is our consideration of a graph that is continuous but not differentiable at a particular point A. So don't think continuity means it's differentiable at a point. It depends on what's going on at that point. Now there's a few other situations where this will be true, so let's go ahead and put up those sketches as well. We can have something called a corner point, which their vertical asymptote, our absolute value graph can be considered a corner point. So we could have some graph that looks pretty smooth and then all of a sudden drops and it has this corner. So this is a corner point. And at that corner point, I have that same problem. I have an infinite number of tangent lines that could occur here. So it's not differentiable at a corner point. Another place that it's not differentiable would be at a vertical tangent line. So let's go ahead and look at that graph. Now a vertical tangent line, there's a couple different ways that you might see that. This is called a cusp, if I can write it in here good. Let me try that again. Kind of comes to this sharp point, almost like a needle point. This is called a cusp. And my tangent line here at that point A would be a vertical tangent line. Now I can have vertical tangent lines other ways as well. I could have a vertical tangent line. This would be a graph of y equal x to the 1/3. And let me get it sketched in correctly here. It almost goes straight up and down. This would be another vertical tangent line. So I have a vertical tangent line here and here. And at neither one of these points where I have this vertical tangent line is it differentiable. So these are not differentiable either. So I'm not differentiable at a corner point even though it's continuous. I'm not differentiable at a vertical tangent line even though I have continuity here. And I shouldn't actually put in dotted lines here because I don't want you to think it's an asymptote. It's actually a vertical tangent line. So it is a line. It's just a vertical tangent line, so it's not differentiable there either. And then of course we have our other case that we looked at already. We have a graph is not differentiable at A if it's not continuous at A. So we could have a graph that looks like this. So if this is the point A, we have a discontinuity at x equal a. And you might say, well, why is that discontinuous? Because the limiting value and the functional value are two different things here. So that goes back to the 3 points of point continuity. So I have a discontinuity at x equal a. So that also implies that it's not differentiable at a. So this implies it's not differentiable at x equal a. So these are the 3 situations where I would not have differentiability as well. And that kind of goes up to this point right up here. Not continuous, not differentiable. And then I have that corner point, so if I wanted to think of this as a corner point as well, or that sharp point, I don't have differentiability at the corner point. I don't have differentiability at vertical tangent lines. And these are just a couple of the graphs that have a vertical tangent line at those points. So those are important ideas. Last thing we want to do is we want to look at a graph, and we want to talk about continuity and differentiability over an interval. So I think probably the important thing is to draw a graph first, and then we'll get started. We don't really need to know any y values for the graph, but the x values will be important. And I want this graph to have a couple of different features. Let's have a filled point. Let's have that hollow point. I want that to come a little bit curvier. Another hollow point. So this is my graph, and these are going to be points, let's say like -1, 0, and 2 are our important points. So what I would like to do is I'd like to talk about continuity and differentiability on an interval. And I'm going to get rid of these arrows on the end. I'll just talk about the graph up to a certain value. So we'll say that this goes to 5, and this comes down here to, let's say, -3. So I'd like to talk about continuity on the interval from -3 to 5. So if I talk about continuity on this interval, we could go back to that nice definition of do you have to pick up your pen when you trace a graph, and we definitely need to. So I can see that I have a discontinuity at -1, and I have a discontinuity at 2. So I have a discontinuity at x equal -1. Now why is that? Because the limit as x approaches -1 of this function does not exist. Why doesn't the limit exist? Because the limit from the right and the limit from the left are different. So I also have a discontinuity at x equal 2. Well, the limit definitely exists because the limit from the right and the left are the same, but what happens here is f of 2 is undefined. So again, go back to that definition of point continuity. Has to have 3 criteria. So 1, f of a is defined. 2, the limit as x approaches a of f of x exists. And the third criteria, if you'll recall, is the functional value and the limiting value are equal. These 3 things have to hold. So I have discontinuities at these points for these reasons. Now let's go ahead and talk about differentiability. So differentiability, and let's do the same interval, -3 to 5. So if I talk about differentiability from -3 to 5, I just have to basically start at my discontinuities, because if it's discontinuous, it's not differentiable. So for this particular graph, to get started, I have 2 discontinuities that I can grab from up above. So, whoops, it's not differentiable. at -1, and it's not differentiable at x equal 2 for the same reason. It's not continuous. Same reason it's not continuous. Or I should say not continuous or discontinuous, but I shouldn't say not discontinuous. So it's discontinuous Okay, now is there any other point that it's not differentiable? And there's one more. So it's not differentiable at x equals 0. And why would that be? Because I have a vertical tangent line. So you have to be able to look at a graph and be able to say why it's differentiable or not, and then for the reason. Now up here, I have a vertical tangent line at this point. It comes to that cusp. As usual, if you have any questions, please let me know. A good graph is really nice to be able to work with. So being able to interpret graphs and create graphs with these characteristics will be very important. If you have questions, you have your Pearson Connect option. You can take a screenshot of your work or the screen and text it to me, and I'd be happy to help. And then also, like I said, we'll be starting some online office hours as well once we get those exam ones completed by the class. Good luck on this assignment.